Nice background music, thank you. Yeah, it's pretty fun, isn't it? I do like just whatever the lo-fi hip-hop thing is, and sometimes it's great, you know? Sometimes it's good. Alright, I'll give like 2-3 minutes. What's up, my Twitch viewers? What's up, guys? Momita and Frozen Fusion. Oh, how do I do the Twitch? Yeah, I had that turned on for my old stream. It's called Social Stream Ninja, is what it's called. If you want to see, I think I can show my main screen here. This is the app, and you can actually. So when I do my my nonprofit tutoring stuff, and if I have enough bandwidth, which I was running into so many issues yesterday with that, just because I think it's because I was running at like 5 o'clock. That's when everyone gets off work and wants to start, I don't know, watching Love Island or some shit. The internet really gets bad. My upload gets bad, but I'll sometimes stream to like TikTok, Instagram, Twitch, and then a couple YouTube channels. I'll do them all at once. How big is my soundboard? It's not that big. It's just a little keyboard. Just like this, right? I have that set up through Ableton. It runs like, if I click a MIDI key, it'll randomly select like what I call like a positive sound, versus like this one right here will select like a negative sound. Yeah, it's not entirely random, right? What's up, Cameron? What's up, Gabriel? Dun, dun. Who's my favorite streamer besides me? I don't. You know, it's so funny. I have a bunch of other friends that I kind of met through Twitch that stream math and science, and I'd say they're kind of my favorite streamers. They're cool. I don't like recreationally, I guess, watch other people's streams. Maybe I should get like a hint for like what's up. Momita says, I have a question. So ask me that during regular office hours, Momita. This is like my physics lecture. So this is where like, if it's directly related to physics, it's okay. But otherwise, Momita, here's the calendar if you want to see, like, that's when we stream like regular homework help stuff. Okay. Give it another minute and then we'll start. That is a Blue Yeti, correct? Yeah, this is a Yeti with a couple like bedazzled jewels on it. And then I have a second one. I don't know if you can see it over here. I think this one's turned off. A little ASMR, yeah. Because sometimes I would do like kind of like podcast episodes. So I'd have someone in the studio here with me, and we would like talk about stuff. Okay, cool. We got a lot to get through today, so I'm gonna try to start as early as possible. It's a lot of fun stuff. Don't worry. All this stuff, I say a lot, but it's a lot of like fun stuff we're gonna go over. So, hang on tight. We're gonna go through all of music in one day. Okay. But yeah, if you have any questions, again, just ask stuff in the chat. What's up, Ace? Yes. Okay. So, welcome to week 2, and this is lecture. What are we at? This is lecture 4. Oh, nice. Okay, cool. We don't have lecture tomorrow, right? It's July 4th. Go enjoy yourselves. You know, have a little vacay time. I don't, Momita, but I can figure it out at some point. Okay, so let me turn off the background music. My bad. Okay, the topic of today's lecture. Yeah, happy 4th. The topic of today's lecture is going to be mainly like music. Okay. And we'll backtrack a little bit on sound. So yesterday we mainly covered the Doppler effect, right? And then how to like characterize waves that way. Here we're going to look at more of the practical uses of everyday sound. So if I was in an actual lecture hall, they have these cool like lab demonstrations that I could show you, and there's some cool stuff, but we'll have to like virtually do it for now. What is there to do on July 4th? Eat barbecue and shoot off fireworks. That's July 4th. But okay. So one of the things that we end up talking about when it comes to sound is sound intensity. I'm sure you guys have seen this. If you ever go to like a concert and stuff, and they talk about like how loud it is at the front, or the decibels that you're hearing. Okay, so sound intensity, which this is again defined as the power being radiated in the wave divided by the area. Remember in yesterday's lecture we talked about how like waves can carry energy, right? And if you have energy and it's coming in at a certain rate of time, right, such as dividing by the period, that change in energy over change in time gets you power. So waves, including sound waves, deliver power, and then that power over area can be thought of as a sound intensity. Okay. And now most sources of sound are what we call spherically symmetric. So that means you have like some central thing here, and then all of the sound radiates out in kind of like a circular pattern. And in 3 dimensions, that's a spherical pattern. So as you get further and further out away from a sound source, okay, let's say this is R, we can say that your intensity is equal to whatever your initial power is. We call this like P0, right? The power here. Divided by 4 pi r squared, because that's the area at which the sound has to be distributed, right? So the amount of sound power from here has to be distributed over the total surface area of a sphere. And if that sphere is located a distance r away, that surface area is 4 pi r squared. So this gives us a cool thing, which gives us like what we say is like an inverse square relationship. So this is called like an inverse square relationship, such that if you double the distance that you are away from a source of sound and source of power there, that your intensity would go down by the square of that. So we say like if you double your distance, that equals a 1/4 of your power, of the intensity. So yeah, so sound intensity drops pretty dramatically as you get far away from something. This is why, for instance, if you're ever at a concert and it's outdoors, they have to put an immense amount of energy into those speakers, because every time you start doubling the distance, you start losing 4 times the amount of sound that's coming at you. When you have venues such as clubs and like indoor things, they get to benefit off of the reflections of whatever the inside of the room to kind of like keep the power in, as well as you have things like wall loading and other effects. So getting a lot of like loudness outside is very difficult, and it's expensive, and it comes down to, because of this rule, that the intensity of sound drops off as 1 over r squared. Okay, so if we want to talk about human levels of like sound intensity, because we need something that kind of makes sense. If I start saying stuff in like watts per meter squared, that doesn't really make much sense. But what we've come up with is the unit of called what's decibels. Decibels, okay. So decibels is how we describe how loud something sounds. And the definition of that is, let's pull it up right here. So physics is the key to DJ. Physics is the key to everything, Fedekai. Yeah. There is a lot of physics in DJing and stuff. And I'll show you, even in like music production, there's a lot of physics. It's really cool. But here we go. So decibels. So you've probably seen this, like dB, like, don't go next to something that's like 100 dB or 105 dB, and you're like, wait, what does that unit come from? Decibels is actually a relative unit. And what it is it's 10 times the log base 10 of the intensity of something divided by like we say this is like the reference intensity. So if you want to know how many dBs something is relative to something else, that difference in decibels measures the log of the ratio of the intensities. And remember, the intensity is related to like the power divided by like how far away you are. But okay. Now, yes, reference intensity is the quietest audible sound. I don't know if it's the quietest, but it's it's a number we came up. Let me see. Is it actually the quietest? I know it's just like it's just a very low value. Okay. Yes, the threshold intensity of hearing. You are correct. Okay, it is the quietest. There you go. This is it. We'll get into later that the quietest audible sound actually varies by person. It also varies by age. As you get older, it becomes harder for you to actually hear things. Well, I mean, duh, but it's actually really cool. It's also kind of like frequency dependent, and there's biological explanations for that. But yeah, so I0, which is usually our reference intensity here, that's equal to 10 to the minus 12 watts per meter squared. And yeah, that's the threshold intensity. Do we use decibels rather than bells since that range best matches human audition limits? That's a good question. I don't know. I mean, we use decibels because deci is 10. And it just makes things like easier, because when we start talking about most common noises that we deal with, it goes from like 60 decibels up to, I think, like 120 is probably like the loudest. Rather than, right, if it wasn't decibels, then it would be like, what, like 6 to like 12, I guess, right? Which is just, I don't know, we like the 60 or something. But here, let me get like a chart of like decibel chart. Let's see if we get like a little decibel chart. Yeah, here we go. That's a cool one. Okay, so here's like not kudu. Nope. Why is it not showing? Oh, you're showing the wrong one. One sec. There we go. Math I do during the week. Abadarajam Haji. That's a very long name to pronounce. Anyways, okay. So here we go. This is, for instance, a range showing what the decibels are for different things. So yeah, if something has a decibel of around 0, that's the softest someone can hear. We get up to 50 or 60. This is like normal conversations. I like how they also say dishwashers. What? 70 or 80, you get to like a police siren, noisy restaurant. 90 is like a hairdryer or a blender. 100, we're getting up to like motorcycles. And at this point, exposure to this level over 30 minutes is dangerous. Like, it'll start causing damage to your ears. And then, yeah, so you start going to clubs. That's like 110. You start going to concerts. That's 120, or like a jet plane. Yeah, and this stuff is like painful. Jackhammers, ambulances, and then, yeah, fireworks and gunshots way up there, like 140. So, yeah, this stuff up here, you definitely do not want to be around for any extended period of time. It'll do bad things to you. Yeah. So, that's kind of like the range of what it is. So it goes, yeah, from like 0 to 140. Usually when we talk about normal decibel stuff, it's like 60 to like 100. That's normal day-to-day stuff. Anything else is like either an extreme or it's very quiet. Okay. But so we can use this equation here combined with the fact that intensity is equal to P over 4 pi r squared to determine what the decibels is for someone, let's say, standing in front of a speaker as they like move away. And this is important for instance, if you're going to a concert. I asked this question when I subbed in and taught this during spring quarter. this year, and it was right around Coachella, and I asked in the class, like, hey, who's going to Coachella? There's only like one person that raised their hand. I was like, what? I guess Coachella isn't as popular as it used to be. But, all right, we have a clicker question based on this. Okay, so let's see. I think if I refresh here. There we go, lecture 8 clicker. Yeah, nice. Okay. We're going to go over this stuff, the helium voice stuff. This stuff is really cool, but we're gonna do that in a second. Let's do this. Yeah, it's a freshman class. I think it's you know what? From my survey, it said majority sophomore. And correct me if I'm wrong. I think Coachella is all ages. No? I remember seeing like children while I was there, which was like kind of like disturbing for me because I'm like, wait, I'm like kind of lit here, and like there's like babies. I put this little meme in here where it says like never forget who was there when you didn't know which stage to go to, because I asked for like the 2 people that are going to Coachella like what their favorite stage was. My favorite stage is Do Lab. It's like not like an official stage, but it's the best stage at Coachella. If you ever go to Coachella, spend all your time at Do Lab. It's great. Kind of not bailing, you know. I get it. Yeah. Although Coachella's over the weekend, right? Although you do get like what we call like the Coachella cough, which
that's dope.
You it's kind of worth it, but then like you're just sick for like a week. Yeah, it sucks. Okay. Here, let me put this over here real quick. One sec. Gotta move some stuff around. OBS giving me issues today. Okay. And then let me get the answer choices. Clicker 8. This is question 3, part 1. Okay. So, it says, at a music festival, you decide to absolutely send it and ride the front of the rail, which is 5 meters from the speakers. The loudness here is measured at 114 decibels. That's really, really loud. It's, like, not very good for you. Yeah, for reference, 100 decibels is, like, the threshold for, like, you'll start damaging your ears if you are prolonged exposure to 100 decibels. And 94 decibels is considered much safer. So it says, yeah, using the decibel reference formula and the inverse square law, how far from the stage should you be for the sound level to drop from 114 dBs to 110 dBs? Okay. So if we use our equation for decibels, right? So this is like, so the original equation we used here, this is like absolute decibels referenced to some baseline intensity, which, yes, we described as the minimum you can hear, minimum decibels you can hear. You can also then rearrange this, for instance, for the difference in decibels between two cases as like delta L is equal to 10 log base 10, and this is I2 over I1. This comes from like the properties of logs, right? So if you remember that, like, let's say like L1 is equal to 10 log base 10, and then we say like I1 over I0, right? And then if L2 is equal to 10 log base 10 of I2 over I0, like these are two different decibels. Watch what happens if I do, for instance, L2 minus L1, which is, we're going to call this like delta L. That would be equal to this, so that's 10 log base 10. Let me put the log 10 on the bottom there. It is calibrated, yeah. It's the number for it, right, is, as we said earlier, it's 10 to the minus 12 watts per meter squared. That's just what scientifically we've determined is the lowest intensity that humans can hear. Okay, so this would be I2 over I0 minus 10 log base 10 I1 over I0. And then we should recognize something. This is like a math concept. If we do difference of logs, remember that log of A minus log of B is equal to log of A divided by B. We should remember this from like pre-calc. It's very, very important. Know this. Then what this becomes, right? This is the same thing as 10 times, we could say, the log of I2 over I0 divided by I1 over I0. And then there's something cool here. Look how the I0s cancel out. And so you're just left with delta L is equal to 10. This is log base 10. Log base 10 of I2 over I1. So if you want to say something has like a 6 dB gain, for instance, then that tells you something about the ratio of the intensity from the thing before it was added to 6 dBs and then to after it was added with 6 dBs. Okay, so we say at the front of the rail, you're at 114 dBs. I want to know, how far do I need to go for it to be 100 dBs? Okay, so first I want to figure out what is the change in intensity if I'm dropping 4 dBs, okay? So here delta L would be equal to -4 because we're going from 114 decibels to 200 decibels. Oh, it should be I1. Thank you, Cameron. Sorry. I think I said I1, but like I screwed up. Thank you. Yeah. Okay, so delta L is -4 because we're going from 114 down to 110. Which, oh, sorry, down to 100, so it's -14. Okay, sorry. I had that wrong. There we go. And then this is going to be equal to 10, log base 10. And then this is going to be, and then we don't have the actual intensity. Okay, but there is something with inverse square law, so I'll show this. Okay, so this would be I2 over I1. Okay, so we can now solve for I2 over I1, right? By dividing by 10. So let's divide both sides by 10. That goes away. And so I have -1.4 is equal to log base 10 of I2 over I1. And then the way to strip logs away from things is to take whatever this base is and then like raise it from that power. So this is 10 to the -1.4. Which, all right, let's pull out a calculator real quick. And so that's going to get us 0.03, or let's just say 0.04, is equal to I2 over I1. Okay, cool. So this is the ratio of the intensities between my location when I'm further away and only hearing 100 dBs to my original location when I was hearing 100 dBs. Sorry, 114 dBs. So the question's asking for how far away from the stage do I need to be? Well, for that, right, we know I is proportional to 1 over r squared. And that came from this, right? I is equal to p over r squared. And this p here is the same for situation 2 and situation 1, right? Situation 2 when you're further away, situation 1 when you're closer, because P refers to the source power of the speaker that it's emitting. And that intensity is dropping off as you get further away. So I can rewrite this as 1 over R2 squared divided by 1 over R1 squared. And now that tells me 0.04 is equal to R1 squared over R2 squared. Okay. And our initial radius when I was riding the rail riders here, is at 5 meters. So I can say, okay, so 0.04 is equal to 5 squared over R2 squared. And now we just solve for R2. So let's see what we get. So I get 25 divided by 0.04. Cool. And then we square root that. And that gets me R2 is equal to 25 meters So that's how far I have to be away from the stage. So that's going to be, yeah, answer choice A, 25.1. Close enough, right? So, yeah, let's put that into Kudu. Let's say choice A for here. Check answer. And we're correct. Good. Okay. Little lengthy on how to solve that. But that's how to do things with decibels. I realize I went a little fast, so let me know if any parts of this were confusing. I think I'm just going to give you the answer to part B because it's the same thing. You just have to like change what the numbers are. Yeah. So it was incorrect for you? Choice A? Really? It says correct for me. For part A? Did you do it for part A or did you do it for part B? Make sure you did it for part A. This is question 3. Yeah, sorry, this is question 3. Sorry, I should have told people. Yeah. This is question 3. Okay, so make sure question 3, part A, answer choice is A. Okay, good. Thanks, Cameron. Okay. Just check it. You get 2 attempts. The next one is then how far for you to be to 94 decibels. So in that case, all that changes here in our math is that instead of going from 114 to 100, now I want to go from 114 to 94. So now that's a drop in 20 dBs. Right? Yeah. So now I would say negative. So here we say, let's do it in a different color. So for 114 down to 94, okay, now you have negative 20 over 10 is equal to log base 10 of I2 over I1. So negative 2, so then it's like 10 to the negative 2. You can. Yeah, you totally can. You can do that as well. It's just, I like 10 to the minus 2. It's kind of like a nice number, right? Because then I have 0.01, right, is equal to 5 squared over R2 squared. And so this ends up being, what's that? That's going to be 25, and then 250, so that's going to be R2 squared is equal to 2,500. And now you just get R2 is equal to 50, right? It's just, these are nicer numbers now. So for part B, here are the answer choices. And then here, let me put part B in there, just so we can see it real quick. So that one would end up being 50 meters that you'd have to go away from the stage. So that one's also answer choice A. Oh, so you get double lucky on this one. Right. So if you click A here, check answer, should be correct. Nice. Again, this was for question 3. We're going to go back eventually to question 1 and 2. I designed these clicker questions when I was subbing in for the spring class, and I had like demos, and it made more sense for me to jump around. Correct. You're right, Fedekai, because sometimes sometimes we get things wrong in like the so if you get like part A wrong and then use the wrong part of that to do part B, you're just gonna be double wrong. So sometimes errors will propagate. So you want to try to like maybe just go back to the original part. Nice. Okay, cool. All right. So yeah, that's decibels and how that relates to hearing intensity and stuff. Okay, cool. So the next thing we want to talk about is like biologically how we hear things. One sec, let me pull, I need this thing down. Yeah, we did loudness. Good, good, good. Okay, cool. Let's do the human ear. Okay, cool. So, and this is also question 4 is what this is. Okay. Okay, so something you may have noticed is that as you get older, it's harder to hear higher frequency sounds, okay? And this is kind of like the diagram of like why that is. So your ear, right, has an opening here, and then there's this thing called this cochlea. This cochlea is actually like rotated like a spiral, but this is like a diagram of what it is expanded out. And what you have is you have these little these fibers that like kind of stick up, and they have a thinner length towards the opening of your ear or opening of your cochlea, and they are longer at the end of your cochlea. And there's some physical reasons, some biological, well, physics reasons for why this is. So if we remember from, let me think, we learned this, right? F naught is equal to square root of ft over mu, okay? So the frequency of these fibers pick up is related to the tension of the fiber and also, like, you know, the mass density of the fiber. So it turns out that closer to the opening of your ear, you have smaller and more like tightly, like less flexible fibers. So the tension in those fibers in your ear is higher. And if that tension is higher, that means they pick up higher frequencies. So that's why, again, the small, tight fibers at the opening of your cochlea pick up high frequencies, whereas the ones deeper in your cochlea that are like longer, they're more flexible, like not as tense, will pick up the lower frequencies. It also has to do with the amount of wavelengths you can fit in stuff, right? And we're going to do that later when we talk about open and open closed. But for now, like, a good explanation is that tiny fibers at the opening are tight, and then big fibers at the end are kind of loose. And that tightness and looseness relates to what the natural frequency is that they can oscillate at. So this question asks, which of the following best explains why higher frequency sounds is the same formula for wave speed for mechanical? Yes, correct. Yeah, it's also the same. Yeah. Yep. You're also thinking about this, right? V is equal to F lambda. Yeah. So here's another cool thing, right? So if the speed of sound is the same, right? This is always this like 343, okay? Then as you go up in frequency, you know that the wavelengths get smaller. And if the wavelengths are small, right, they're more likely to match these small fibers. Versus for low frequencies that have very high wavelengths, right, really big waves. Remember we talked about how like a bass wave is like 6 meters long? You want your fiber that's trying to pick up that sound to also be long, because it has the best chance of trying to capture all that information. Now, I wonder if I can do this. Let me see if I can do this. If there's like a frequency generator on the web. I wonder, yeah, okay, here, online tone generator. Let's just see if we can get this to work. Okay, cool. I would do this in lab. I would have like a signal generator, and we would just like start cranking the frequency up, and we'd see like what you can hear. So I don't know how loud this is. I hope it's, oh, here's a volume thing. All right, so let's start with like 440 hertz. Okay. So this is a standard 440 hertz signal. We can go up to, let's say, like 5,000. Are you trying to mind control us? Maybe Nico. Okay, can everyone hear this? I'm going to keep going up, and then you tell me when you can stop hearing it. Tell me like what number. We're up to 8. I still hear 8. 9. Fat guy says no. 11. 12. Oh, now this is getting hard. Asa says, oh no. Okay, I cannot hear this. Can anybody hear this? We're also testing whether I'm allowed to stream above 16 kilohertz. Usually most like software stuff. Yeah, this might be yeah, okay, all right, we're gonna stop. Okay. This might be, unfortunately, a limit of the electronics here. A lot of times, in order to save information, a lot of broadcasting software won't let you do anything over 16 kilohertz because barely anybody can hear it. Try 15999? Maybe. I think this is a software problem. Oh, actually, I can hear this. Yeah, tell me, can you guys hear this? I can't smell anymore. I can barely hear this. This 15999. Yeah. Barely. Okay, cool. Yeah. So, again, if I was to do this in class, because I'm older, I'm 35. Most of you are like maybe hit 20 at this point. There is a significant difference in like what frequencies I can hear and what frequencies you can hear, for those that are younger. And it has to do with there's this degradation of our fibers within our ears as we get older. It's pretty cool. It's a really fun lab demonstration that they do. But okay, so I can't hear past 7,000. Am I cooked? Maybe wear more earplugs when you go out to concerts. Okay. Anyways, these were the answer choices for why high frequency sound waves are more likely to be lost due to age-related hearing degradation. And this is question 4, guys. So for those of you answering, right? So in this case, the answer is going to be D. And it says higher frequency waves stimulate the base of the cochlea. The base is considered like the beginning of the cochlea. And that's where hair cells, right, are the closest to the opening of your ear, right? And so that's where those are most likely to get damaged from, I mean, a number of things like dust, loud sounds, I don't know, like you went in the ocean too many times, you got like flesh-eating bacteria. So, yeah, the reason why is that stuff closer to the opening, which is the high-frequency stuff, is most likely to get damaged, and that causes you to lose that side of your hearing. Okay, so that was question 4. There we go. And so that answer choice is going to be D. So let's make sure that's correct. Good. Okay. And then, cool, here's like a nice little follow-up question, which I think we kind of explained this already. Question 5. So here we're asking, why do high-frequency sounds primarily stimulate the base of the cochlea, which is like the early part of the cochlea? So the correct answer for this is B, right? So as we talked, right, the high-frequency ones are stiffer and they're narrower, right? So that increases the natural frequency that they absorb. And then, yes, the speed of the wave within the fibers is then faster, okay? Remember that the speed of sound is the same as long as it's in air, right? But once that sound is absorbed by the membranes, the little fibers, that speed of sound will change. That wave speed will change based on various things such as, the tension and the length of them and stuff, yeah. So, yeah, answer choice here is B. Yeah, when they say low frequency waves reflect at the base, that's not right. Like what? No. Low frequency goes all the way in. The apex acts as a high pass filter. No, I don't think that either. And wave speed is slower due to increased damping. Well, if anything, there would be decreased damping because it's the closest to the opening. So, yeah, correct answer here is B. It has to do with the stiffness and that creating like a higher natural frequency for the waves. So to question 5, that should be answer choice B. And did it want? Good. So that's correct. Nice. Okay. All right, we're going to do beat frequency in a second. Let me figure out what I want to teach y'all next. Yeah, let's do the, okay, let's talk about, again, if I was actually in person right here, they would give me a tank of helium, and I would inhale helium, and you would notice that my my voice gets higher. It would probably,
you know, sound something like this if I were to take a tank of helium and then just start talking to you. Actually, during class, I had the students like tell me the song they wanted me to sing, and I just like ripped some helium and started talking like this.
Yes, the baby voice command, it is real. So yeah. So the question comes up here is like why does that happen, right? Why does the pitch of someone's voice sound higher when you start inhaling helium? Okay, and let's see. There's some common misconceptions from why this is. Okay, my voice is normal now, right? Did I exhale all the helium? All the digital helium? Okay. What is the main physical reason for this change? So, a lot of people do think that that your vocal cords change, and that's actually incorrect. So there is no change to your vocal cords. I don't know. That's also what I thought when I was first like teaching this. I was like, wait, yeah, doesn't like helium like affect the vocal cords? Turns out it doesn't. So how like the human voice works? Okay, so let's say we're here and we're singing. Okay. You have kind of in your throat, you have what's called like a diaphragm, right? Which is like a resonant cavity. Also, yeah, diaphragm, I guess, right? I think that's how you spell diaphragm. And then inside here, you have like your vocal cords. And your vocal cords like vibrate, right, back and forth, and that's what creates sound. Is they're creating like sound pressure waves within your diaphragm, like right by your throat. And when that happens, right, you're always going to get like some bass frequency, some key frequency, we would say, like, right, which is like F naught. That's the bass frequency. But then on top of that, you will end up getting different harmonics, and these harmonics are called formants. So this is the bass frequency, and that's strictly due to the movement of your vocal cords. But then you will also get kind of like some like higher frequency things that happen, and those are called formants. And these formants depend on the geometry of your diaphragm. Okay? So that's what gives us all, like, you know, everyone's voice like sounds different and whatnot. The main reason for that is that our diaphragms are all different. And so the geometry and shapes of them create like this unique, they call it timbre. It's kind of like flavor or like color to sound. But there's a unique timbre that each one of us has with our voice. And it comes from the formants, or these individual harmonics that are created because of whatever the geometry of our diaphragm is. And because we're all unique and different, right? We're all special. But the bass frequency here that is being generated, okay, that stays constant no matter what medium is within the diaphragm. However, when you inhale helium, let's remember that helium is much lighter than air, right? This is lighter. Okay. And something that is lighter, oh, someone's correcting me here. Diaphragms are below our lungs. Vocal cords are in the larynx, which is the top of the trachea in our neck. Oh, okay. So ignore my biological diagram here might be a little bit incorrect, but the way I understand it is you got vocal cords, and then they create sound that resonates. Not in the, I guess, is it not the diaphragm? Is that the diaphragm of our chest? Okay, well, let's just say it's the resonant cavity. It's the place above your vocal cords that things resonate. Okay, so since helium is lighter than air, this means that particles travel faster. And if particles travel faster, right, they're able to collide into each other more frequently. This leads to a higher speed of sound, okay? So sound travels faster in lighter air, right? In helium that has like more collisions and they happen more rapidly, right? That only affects the formants, okay? So it affects the frequency of the formants. It does not affect the bass frequency that is being produced by the mechanical motion of your vocal cords. Yes, we are changing the medium in which sound is traveling for. Exactly, right. So the correct answer for this is choice B, and that's because, yes, the speed of sound increases, and it shifts the vocal tract. Maybe this is called the vocal tract. Santrix, maybe it's called vocal tract. Again, this is not a biology class, but there's some cool biology to this. And that will shift the formant frequencies upwards, right? So the vocal cords do not vibrate faster in helium. Vocal cords vibrating is a physical thing that your body just does. I'm sure it like experiences like slightly less resistance with helium, but it doesn't really change it that much. Because the fundamental frequency, Sib, is determined by the physical motion of your vocal cords. Yeah, okay? So, no matter what the medium is in there, your body is still exerting like a certain movement to it. It just knows what to do. Helium adds harmonics. That's wrong because your voice already has harmonics no matter what medium it's in, and that's due to, again, the geometry of your vocal tract. And then the vocal cords become lighter. No, the vocal cords are the same weight. They don't change the weight of your vocal cords. So the main reason is that the speed of sound increases, and then that shifts the resonant formants upwards. So for question 1, that should be answer choice B then. Is she working today? There we go. Nice. I guess my Wi-Fi is kind of McDonald's today. Okay, here we go. So then question 2. So this is actually a good follow-up question, right, Sib? You were kind of asking this, which was, why does the fundamental frequency of your voice not change significantly when you inhale helium? And right, so they say here, what, the fundamental frequency is determined by the vocal tract, not the cords? That's incorrect. Fundamental frequency is dependent on the physical motion of your vocal cords. So that's this. That's wrong. Helium changes only the mass of the air, not the mass of not the vocal cords. I mean, that's like kind of correct, but it doesn't really explain it completely. The properties of vocal cords remain the same regardless of the surrounding gas. This is true. I agree. Some people argued in class. They're like, wait a minute, but isn't it easier for the vocal cords to vibrate back and forth if the gas is lighter? And like, yes, but I think in physics land, we say that's not like a significant difference. It's not a significant change. Again, sometimes that's like kind of hand wavy. You're like, okay, bro, but what's significant? And then helium stretches the vocal cords. No, that's not right either. So the correct answer choice for question 2, that's going to be choice B. Okay, let's do it. Yeah, it's choice B for question 2. Good, and that's right. Nice. Okay, let's see. So we got through 1, 2, 3. We got through 4, 5. Okay, we got to do beat frequencies. We'll do beat frequencies. Before I do that, I'm going to show you guys something cool, kind of like music production land. Does anyone here use Ableton, for instance? Does anyone know what this software is? It's kind of like music production software. But what you can do in this case, we can this is called a synthesizer. You used to, cool, Gabriel. So this is how we can generate waves. FL Studio, that was my first. It's called a DAW, digital audio workstation, yeah, or workspace. Yeah, FL Studio was my first. Your teacher used to use it. Very cool. Yeah. So here we have, for instance, this is called a saw wave that we can just generate. So I'm going to turn the volume down and make sure this isn't too loud for you guys. Here we go. Let's see. Okay, cool. Do we see that? Yeah. So this is generating. We're clicking on my little keyboard here. See it right here. But we can generate saw waves, right? Anyone remember Swedish House Mafia? Okay, but from this constant wave, we can now apply filters. And one of the filters that you can select is called a formant filter. And I'll show you how a formant filter, which simulates the resonances in our vocal cavity, kind of sounds like human voice. It sounds like talking. So, for instance, here's a steady wave. And now I'm going to turn the formant on. And so, yeah, it's these little peaks happening at these mid and high frequencies. It sounds like a robot speaking. Yeah, this is what creates human voice. Is those resonances, those formant resonances. So you can think about the unfiltered signal, that steady buzz, as being what your fundamental frequency is, and then the formants are all the resonances that happen in your vocal tract, and that's what creates speech. Yeah. Cool. All right. I hope that was a cool little demonstration. It's as close as I can get to doing lab demonstrations in this class. Okay. The other thing we can go over is called beat frequencies. How cool. Thanks, Sib. Yeah, that's cool. So beat frequencies occur when you have two waves at slightly different wavelengths, or slightly different frequencies, creates another wave that is the difference of those frequencies. So, for instance, if you have a source here, let's say that's playing at 440 hertz, and then you have another source here that's playing at 448 hertz, these two will interfere, just of how the phasing works, right? One's going faster than the other. So at certain points in time, the waves will line up with each other and create peaks, and at other points they'll cancel each other out, and that'll create silence. But that will occur at a difference of 8 hertz. So if you have a 440 next to a 448, you will hear something that's oscillating 8 times per second. Oh, and we can actually demonstrate that. Let's do it on the tone generate. Wait, what is this stuff? I don't want to install ads. Okay, here we go. All right, let's take this. I'm not going to torture you guys with the 1600, but let's say we have our sine wave at 440, right? Okay, I'm going to duplicate this, and we're going to play another sound. Let's say at 442. You hear how it goes woo 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 woo. And watch as we crank this up. Let's crank this to let's say 445. Do you hear how it's oscillating like more? You can do like 448. And then if we get like really close to it, let's go back to 441. Hear how it's like coming in and out, in and out. That is, yeah, that is beat frequency. Is that how vibrato works? Not quite. As someone who plays the cello, vibrato works because when you press your finger down on the string, you're slightly bending the position of your finger up and down, and you're doing it back and forth and back and forth and back and forth. And so that's like manually creating vibrato. Do they have to have the same amplitude? They don't. I mean, you'll always notice the difference. So, Sib, if they're the same amplitude, you will hear periods of double and periods of nothing, right? But if they're at two different amplitudes, then they won't ever like perfectly cancel each other out per se. I gotta think about that. Wait, I guess they would actually at certain points, right? But okay, actually no, right? If you had a wave that was like twice as high and something that's only like 1 times as high, that other wave can only cancel out half of the other wave, if that makes sense. So if you had, for instance, this, which is like 2 amplitudes, and then you have like a beat frequency on top of it, right, which is only like 1 amplitude. I think you definitely you hear this 2 amplitude wave a lot more, and this 1 amplitude wave would only like diminish it like a couple times. Yeah. So the beat frequency, it wouldn't be as drastic. You wouldn't be going from 0 to high, 0 to high. You'd be going from like medium to high, medium to high. So it's interesting. If they're different frequencies, they're naturally gonna always like reach some out of phaseness, right? Because one's traveling quicker than the other one. So they're always playing catch up with each other. Right? If they have similar amplitudes, the effect is more pronounced. I mean, we can do that here. Well, so for instance, here's the 440. Here, let's do the 440 at like a really low amplitude. And then let's do the 441 like double it. Do you hear how like the difference, like the beat frequency doesn't cut out as well? But if we match it, you can get points of complete silence. Because yeah, they're the right frequency. Not they have enough amplitude to cancel each other out. Yeah. Okay. So, yeah, so beat frequency depends on the difference between 2 frequencies. So, let's go to question 6 here. What are we doing on time? All right, still got 15 minutes. I think we got enough time to go through this. All right, cool. I think also, I cut a couple questions, but when I did this was for a lecture that was an hour and a half. Or actually, no, I think it was almost 2 hours maybe. But okay, here we go. So it says, a violinist is tuning her A string and playing at the same time as a tuning fork that sounds at 440. While playing, she hears a beat frequency of 3 beats per second, right? So 3 hertz. What are the possible frequencies of her string, right? So remember that beat frequency is the difference between 2 sources. So if I'm hearing a beat frequency of 3 and one of my sources is 440, that means that you could have something that's at 443, because that's a difference of 3. Or you could have something that's at 437, because that's also a difference of 3. So yeah, the correct answer for this one would be D. Okay, very cool. We got that done. All right, we only got 3 left. Okay, let's go into... I gotta talk about open, open, close, closed, open, closed, all that stuff. Where is she gonna be? Okay. Okay. Yeah, okay. Open at both ends. we do closed at both ends? Okay, so we earlier talked about kind of the normal modes of what happens when you have like a piece of string, right? And it's like fixed at both ends, right? And we talked about like what wavelengths you could fit in there, right? So due to these boundary conditions, if these are both fixed, you ended up saying, okay, cool, I can fit half a wavelength, or I could fit a whole wavelength, or I could fit 1.5 wavelengths, right? So we could, let me see how this works. Like that. There you go. So that's a way. These are all the different ways you can fit, and these are harmonics, or what these are called. Like higher and higher frequencies that are allowed to exist between 2 points that are fixed. So now let's consider the case of it being fixed on one end, but being open on the other. So if you've ever done this with, for instance, like a glass of water, and like, you know, if you blow into the bottle or something, that's an example of where we have closed, open, okay? So if you have sound waves being closed at one point such that they're fixed here, but they're open here, now what the boundary conditions means is that this ends up having to attach at the edges here. So this is a quarter of a wavelength, okay? And the multiples of this that you can put in, for instance, the next one would be 3/4 of a wavelength. Okay. Think about, like, as I draw my wave, right? If I need it to be at a node here and then an antinode here, one way to do that is a quarter. I can't do half a wavelength, right? Because that would be a node and a node. But I could do something like this, right? Oh, well, they draw better here. Where now, again, you have node, you have antinode, but this represents what 3/4 of a full wavelength would be, okay? And then these patterns go up and up and up, and you start seeing that they are odd multiples of each other. So these are kind of the higher and higher harmonics that are allowed to exist in something that is closed and then open. So you can have a quarter of a wavelength. You can have 3/4 of a wavelength. You can have, what is this, like one? This is 5/4 of a wavelength, 7/4 of a wavelength. All right, and then if this length of this cavity or this resonant thing is length L, okay, you can then solve for what the wavelength would be, right? Because if a quarter of a wavelength fits in a distance L, right? So if 1/4 wavelength fits in a distance of L, that means lambda is equal to 4L. And then here it's equal to 4/3 L, and then 4/5 L, and then 4/7 L. Which, if we then use our equation of, right, V is equal to F lambda, you can then solve for F. So in this case, right, since V, or this is the, let me put this all in here. This is the first one. Since V is equal to F lambda, that tells me that F is equal to V over lambda. So that's going to equal to V over 4L. But let's go to our first overtone, right? In this case, you have 3/4 of a wavelength fitting in L. So that means that lambda is equal to 4L over 3. And then if V equals F lambda, that means F is equal to V over 4L over 3, which is equal to 3V over 4L. And notice this is 3 times this one, okay? So this they call here the first overtone, or I guess the second harmonic. So this F2 is now equal to 3 times F1. And you can go on and on and on. And what you end up noticing is it goes like 1, 3, 5, 7. So the third harmonic is going to be 5 times the first one, and then this one will be 7 times this one. As opposed to when we did closed, right? In this case, it was like F2 was equal to twice F1, and then F3 was equal to 3 times F1, and so forth. Turns out that closed is the same thing as open. So this right here, this is closed. You can also have open. And it's kind of the same thing here. You can fit half a wavelength in here. Then you can fit a whole wavelength, right? And then you can fit 3 wavelengths, 3 halves of a wavelength, and so forth. And that gives you the all the whole number multiples of F1. So this is like twice, 3 times, 4 times, 5 times. Versus for open, you only get 3 times, 5 times, 7 times, 9 times what the initial frequency is. Okay, so for the clicker question here, where we say, given 2 wind instruments of identical length, one is open at both ends, whereas one is closed at one end, which one's able to produce the lowest frequency? Okay. So let's remember, right? So for open, closed, you have that you can fit a quarter of a wavelength in some distance L. Whereas for open at both ends, which is the same thing as closed at both ends, that gives you half a wavelength is equal to L. So in this case, this tells me that wavelength is equal to 4L. Here, wavelength is equal to 2L. And if we remember what the relationship right between speed and wavelength and frequency, so V is equal to F lambda, so that tells me F is equal to V over lambda. So whatever has the bigger wavelength will have the lower frequency. In that case, open closed has the bigger wavelength. So it can produce a wavelength, it can support a wavelength that's 4 times its length, whatever the device is. Versus open or closed can only support twice the length as the lambda. So the bigger lambda is the lower frequency. So that tells me that open closed is the one that can support the lowest frequency. So for that one, that's going to be the one with only one open end. That's going to be choice C. Good. And then cool, here we have another one, which has to do with the harmonics. Okay, so it says a tube is driven by a speaker, displays resonances at 450 and 600 with no resonances in between. The fundamental frequency was found to be 150 hertz. What are the boundary conditions on the tube? Okay. So the fundamental frequency is 150 hertz, right? So F1 is equal to 150 hertz. And then we know we have like some multiples where we have 450 hertz. Sorry, this is capital H. And then we have another resonance or harmonic at 600 hertz. And we want to know whether this can be open, closed, open, closed, or open, and closed. So let's consider like what the multiples this is of our fundamental. Here, this is equal to 3 times F1. And then this is here equal to 4 times F1. Well, I know if something is open, closed, that I only get the 1, 3, 5, 7 multiples of the fundamental frequency. Right? That's what we had from, where did we do it? That's what we had from here. right? This was the 1, 3 times, 5 times, 7 times. So since this one is 3 times it and then 4 times it, that only occurs when things are open, open, or closed, closed. The key thing is they also said there was no resonances in between here, right? So it's not like this is going to like 3 times this and then 5 times this. So in this case, this one is going to be open, open, or closed, closed. If, however, your frequencies of your harmonics, let's say like a counterexample, if you had 450 hertz here, okay, and then you had 750 hertz, this would be open, closed. Because in this case, this one is 3F1, and then this one is 5F1 for the next harmonics. And so when they're the odd multiples, that's when you have open, closed. When you have sequential multiples, like 1, 2, 3, 4, 5, 6, like you're including the evens as well, that's when you're either open, open, or closed, closed. So correct answer for that one is going to be D. Question 8. Cool. Okay, good. We're doing good on time. I apologize. There's a lot of material to cover in an hour and 15 minutes. But if you have any questions about this stuff, please come by office hours early next week, and I'm happy to go more in depth with things. I just want to make sure we get through the clicker questions at least. Okay, so question 9 here says, what length should a bagpipe have to produce a fundamental frequency of 119 hertz? Assume the pipe is open at both ends and being played at room temperature. Okay, cool. So let's remember that when things are open, open, right? It's the same thing as closed, closed, which means that your fundamental frequency, the lowest frequency wave you can get there, is where you have half a lambda is equal to L. Okay. So I say, okay, cool. So lambda is equal to 2L. But I want that frequency to be 119. So remember that F lambda is equal to 343. So that means 119, which is my frequency, times my wavelength, which is 2L, needs to equal 343. So if we take our calculator and do a little math on this, right? So I'm going to do 343 divided by 119. We're going to divide that by 2. And we're going to get that L is equal to 1.44 meters, right? So that's going to be answer choice B. Okay. Right, let's put that. Is that correct? Yes. Nice. Okay, good. We got that one correct, so that's good. Let me see. Is there anything else I wanted to quickly go over before we got to things? No, I think that's it. Oh, here. So the reason why I asked this question about the bagpipes is my dad plays the bagpipes, and I used to play the drums with him while he was playing the bagpipes. And so here I got a super old photo of me and him. This is when I was in, I think, high school. Yeah, but it's me in a kilt, which is always kind of funny. So there you go. That's me and my dad. Very nerdy Dr. G. And we played in these funny outfits, but I would play the snare drum and he played the bagpipes. And I always had to tune this thing for him. Bagpipes are very difficult and they go out of tune all the time because they have, let me see it, a little diagram of the bagpipes. Bagpipes diagram, how they work. Yeah, you have these things, these drones. Yeah, so in the bagpipes, you have these are columns, right? And what you do is you adjust the length of these columns in order to produce different frequencies. And you want them all to kind of produce like this one like bass note. And so you have to, someone here who's playing the bagpipes has to like constantly breathe and like squeeze. And then it's a two-person thing. Someone has to come behind and like start moving them so that they're in tune. So anyways, little tidbit. Okay, that's it for today. I hope you guys enjoyed today's lecture on sound and music. Again, no lecture tomorrow. It's a holiday. Have fun, eat, be merry. Don't hurt yourself with fireworks. We will resume lecture on Monday. I'll post a new chapter over the weekend, so you guys can get a start on that. And then I'll also post information about what the exam's going to be next Friday. So yeah, great, cool. Okay. Enjoy the weekend. We will see you guys on Monday. Feel free to post on Campus Wire if you have any questions about other things. Peace.